Alright, so today we're working with these things called complex fractions. We should probably try to figure out what they are. And it's really easy to see what they are. Consider this 3 over 5 over 5. This is a fraction, and the thing about this fraction is that at the top it has a fraction, and at the bottom it has some number. So in this case, what it is a fraction of fractions in some way. So this is what we would call the complex fraction. The name is a little bit deceiving. It's not that it's complicated, it's just that it's a fraction where the top or the bottom may be a fraction. Here's our other examples, such as this. And we'll soon begin to learn how to work with fractions, but these are just a few examples of them. Fraction over fraction, number over fraction, fraction over number, fraction over fraction, blah blah blah. Bunch of things that have fractions over a bunch of things that have fractions, and so on and so forth. Those are complex fractions, and so let's get right to it. First thing, how do we learn to deal with them? So we're going to take them and break them up into two different categories. The first category is where the bottom is actually just some number, and the top is the one that's a fraction. If that's the case, well, we already have the tools to deal with that. Let me remind you, this is a little reminder, when we have a fraction a over b, what is the definition of a over b? Really, we have no business talking about complex fractions if we don't even have a good definition of what a fraction is. And fortunately we do. A fraction a over b means a times the multiplicative inverse of b. That's the definition of a fraction that we adopted. That's powerful because here that means that this means 3 over 5 times 1 over 5. That's by definition of fraction. And now we just multiply fractions by using our multiplying skills, multiply across, and that gives us 3 over 25 by math. So the case where the bottom is just a plain number is incredibly easy. If the top is a fraction, don't even worry about it. You can just put it off to the side using the definition of a over b. That was easy, right? Let's take a look at another idea. What if the bottom is not a fraction? What if the bottom is actually a fraction? Well, in that case, we'll handle it two different ways, okay? Here's the first way. You could say, well, that's the same thing as 3 over 5 over 7 times 1 and then times 1. Or said differently, wait. So the case when the bottom is a number is easy. You just bring this to the side and you're done with definition of a over b. This case requires a little bit more thinking, maybe. I'll do it a couple different ways. First, I'll do it here. Yeah, I'll do it right here. 3 over 5 over 7 times 1. This is by multiplicative identity. I can always multiply by 1 and nothing happens. No, the value is not changed. Then I write the 1 in a clever way so that I can kill the denominator, and I use the fact that a 7 over 5 would kill a 5 over 7. Together they would give me 35 over 35, which would be just 1. That's the killer of 5 over 7 is 7 over 5. Sometimes they call that the reciprocal. And so this justifies it because this is just 1, a number over itself. That's by just 1. And then I multiply across, so I have 3 over 5 times 7 over 5 all over 5 over 7 times 7 over 5. That's by math. And then I do that by math again, so that becomes 21 over on the top 25. On the bottom I have 7 times 5 is 35. 7 times 5 is 35. That's by math again. The bottom becomes just 1, so that's 21 over 25 over 1. That's by just 1 theorem. I changed this one right here, the 35 over 35, I changed it to 1 by just 1 theorem. And now I go with 21 over 25, and that is by out, the 1 under theorem. The 1 under does nothing. And there you go, I was able to simplify it. Now, you could repeat this same thing over and over again, and you could establish this as a pattern and maybe package it into one theorem. And to package it into one theorem, look at how we do this using just generic letters. If I have a over b over c over d, if that's given, I can always say this is a over b over c over d times 1. This is by multiplicative identity. And I could always rewrite the 1 in a clever way so that I could kill this thing, c over d. Well, that would be d over c over d over c. That's by just one theorem. And then I could glue them together and I get a over b times d over c all over a cd all over dc. That's by multiplying a cross theorem a couple times. But this is CD and that's DC. I can switch those over and that becomes A over B times D over C all over. I'm going to switch these CD over CD. That's by commutative law of multiplication. And now the bottom is just 1. So I have A over B times D over C. The bottom is just 1. It's just one theorem. And of course I could drop that and I get A over B times D over C by the out theorem. And so we package all these steps, and they say the following. If I have a fraction a over b, and I have some denominator here that's also a fraction c over d, look at what happened. Focus on the beginning and focus on the end, because these steps will always be the same. We can package them. Focus at the beginning. A over b, c over d became a over b. The top just remained the same. The bottom just got flipped, and we changed that to times. That's what we're going to package. It's called the flip the bottoms theorem. So you take the bottom and you flip it. FBT. FBT. Flip the bottoms theorem. Okay? So, again, all you do is take the bottom and you flip it. That's the case when the bottom is a fraction. If the bottom is a fraction, you can always flip it. And that's a proof right there. And there are other proofs. Maybe I'll show you more proofs later. Maybe not. Maybe I'll let you think about a different proof. Maybe even shorter, nicer, cleaner proof. Just for fun. Alright. Next, let's use the flip the bottoms theorem to simplify some fractions, alright?